I think we talked a little bit about the idea of a workshop beforehand, and so a lot of the views we're going to put forward are our own. I haven't discussed anything that I'm going to talk about, so hopefully you will disagree with a lot of what I'm going to say. And we're going to present a lot of different things. So having said about high field, I'm going to talk about low field. Then we're going to have Klaus then is going to talk about high field. So we'll try and present as many different views of what we see as being important in the future. So I think as I was listening to the introduction, I was thinking, God, I am old, right? I mean, all of those dates that came in from the past. So as sort of leading off, I'm going to give a little bit of a historical perspective then on what we see as technical developments, and then to try and project those into what I think would be a nice sort of next 10 years in terms of MRI. So I was reading an article just last week in The Guardian, which is one of the very few newspapers you can actually still read. And there was a columnist who was looking at technology, just general technology, and how that's developed over the last 20, 30 years. And he had an idea of putting these not as a sort of continuum, but into different epochs. And he sort of came up with 3 different epochs. The first one was looking at the PC coming in, and he had this roughly 15 years each. Then the second thing was the internet era coming in with everything that comes into now, streaming, etc. And then the third epoch was the mobile phone. And the idea was that these were technologies which are obviously related, but in what they allowed you to do and the philosophy behind those, they were fundamentally different. And one of the things he said, which I thought was interesting, is the future, which we're going to try and talk about today, it's already here, right? We're not going to suddenly discover something that pops out of nowhere. But it's sort of not particularly evenly distributed. So across different scientific, across different social areas, these ideas are here. But there's something that sort of comes together where things coalesce into something that forms what he had as these epochs. So I thought, again, just to try something different, something new, that I try and define our own technology epochs in terms of MR, and then see where that leads to in the future. So this is very, very pretentious, right? So to start off with, and this is, I think I'm probably one of the few ones who was actually present during this, from the start of MR as a commercial, let's say, rather than scientific, into mid-90s, what happened was really concentrating on the hardware there. So we went from we went to 1.5 Tesla superconducting magnets, which could be reproduced by the companies. All the electronics, which in the early 80s were terrible, awful, noisy electronics, they got developed by electrical engineering departments. So we got to sort of low noise electronics. Our gradients got to reasonable values where the sequences we designed we could actually play out in practice. And then finally towards 1992, then we had these phased array coils. In other words, we went to a multiple detection system. And so this epoch really took us from a very low signal to noise imaging technique to one which was pretty optimal in terms of that. So we were getting the best signal that we could get out. But at this stage, imaging was extremely slow, right? So we were having to cover, as we acquire MR data in reciprocal space, we had to recover all of that reciprocal space. It was a very, very slow scanning process. So what you were able to do from a clinical point of view was relatively low resolution. It took quite a lot of time, and you might have only 2 or 3 different contrasts in your design. And so what this allowed us to do was to go for one on the left. So I'm going to choose two images from Leiden. So this is the first image that ever came out of Leiden on the left, 1983, to one that comes out, of a standard sort of Philips scanner. And if you look at the corresponding hardware then, this was the first scanner on the left, which actually I think looks a lot nicer than the one on the right, right? I mean, the use of wood in a scanner has to be good. But you can see the progression then, and that just leads, the basic physics is the same, but all of the hardware changes then allowed you to make this fundamental leap in terms of image quality. And then we come to sort of the second epoch, and this is where people started to think more about how do you actually acquire the data. And so you went to very fast and efficient sequences, so things developed, for example, by Klaus Scheffler. We went to this concept of parallel imaging, right? This was the first time where we didn't just try and acquire all the data that was necessary, right? That we were able to subsample, to undersample the data. And then by using the fact we had multiple receive coils, we could reconstruct the images. And I'm hand-waving here not to go into too many details because this is areas that other people, for example, Nicole, will talk more about. So, but the fundamental idea was we could undersample data, and that made things faster. And then we had to have the image reconstruction to be able to have artifact-free images. So suddenly here, we were able to acquire more data at higher resolution, and fundamentally, this idea of data undersampling. And so just to give some ideas here, some examples here then, you would basically use spatial information from having more than one receive coil, and you would build that into inverting your matrix in order to reconstruct your images. So rather than have aliasing, because you're undersampled, you were able to overcome that aliasing and to come back to fully reconstructed images. And as I said, I'm going to use some slides from Siemens because I'm a Philips user, and so I have to try and be fair here. What this allowed you to do, if you just look at the sort of pink here, the time that you were able to acquire these images suddenly become much, much less. So take on the left-hand side, rather than a 15-minute scan, you now were a 4-minute scan. So this means image quality went up because you could either acquire higher resolution images, you had more chance of the person not moving, but you could also add more contrasts. So the idea of undersampling from a clinical point of view gave us this really much increased capability in terms of MRI. And then some of the work that, again, Nicole was involved in, if you can image faster, things like if you're asking the patient to hold their breath, intrinsically you're getting higher image quality. So this was really a major development. And I think, interestingly, if you look at the speakers who come after me, one of the things that you'll see is that almost all of their technical developments are now in real clinical practice, right? And that's very, very rare for those things actually to be adopted by commercial companies and to be used now effectively on every single scanner. So let's look at the third epoch coming up to the modern day. So Klaus will talk a lot about ultra-high field and the promise of ultra-high field, MR, 7 Tesla, 9.4, 10.6 in Minnesota, lots of plans for European 14 Tesla systems like that. It's a steady progression going up. For me, the thing that really changed here was that we went away from very analytical ways of reconstructing data into model-based reconstruction. Things like compressed sensing, which Mickey Lustig developed, MR fingerprinting, which Nicole was heavily involved in. Effectively, we were now acquiring data. We didn't have to acquire data according to a certain pattern. We could acquire data how often we wanted, in whatever kind of directions we wanted. We could acquire it continuously, so we sort of borrowed from the ultrasound field, where they just basically acquired data nonstop. And it came into then being able to reconstruct that if we had a good model of the system that we were trying to reconstruct. And then the last part here, we start to see this, right, that we're integrating AI, particularly into processing of data, but also starting to put that into the acquisition of data. So we go again from a system where we were undersampling, but in a fairly standard, conventional way, to now where we can really design completely arbitrary ways of acquiring our data. And if we've got a good model of what we're trying to reconstruct, we can again undersample by even more. So things get even faster here. And so again, just to give some example, this comes from Mickey's work here. The whole idea then from Donahoe of randomly being able to undersample, and when you reconstructed there that all of your noise over here also was randomly distributed, rather than giving you structured undersampled artifacts there, it became random. And so by choosing again case space on the right hand over here, you can see even with randomly undersampled, we're able to reconstruct images. And so again, this gave us another big increase in terms of how fast we could image. We had the fingerprinting idea, which again, coming from Mark Griswold's lab and carried on by Nicole and various others, where again, we're basically trying to match evolutions of magnetization. So it's a different concept here. So massive undersampling of the data, enabling you to get quantitative MR, which might not be such a good idea, as Nicole will talk in the next presentation, just by matching patterns rather than acquiring data in the usual way. So lots and lots of different ways of being able to acquire data. And again, this was some results from the Facebook challenge. So Facebook had put a challenge up saying, here's some undersampled data. Everybody should develop their own algorithms to be able to reconstruct these. And again, you can see that if you compare it with just a very simple reconstruction on the left over there, you get pretty good reconstructions there. Although I'll come back to some of the problems with AI or some of the things we have to be careful about. And there's just a recent paper, I think last week, from Mickey's group, which really shows that you have to be very, very careful. It might look very good, but often you lose the actually critical information that you're involved in. And that's going to be, I think, one of the things we have to look at very, very carefully in the terms of the role of AI in the future. But if you summarize all of this, what it means is that MR, over the last 20 years, has gone from a technique which gave you great information, but relatively little information acquired in a very conventional way, to one that has been radically speeded up. It means you can get very high resolution. It means you can do lots and lots of different contrasts, whether that's in a clinical scan or whether that's in a research scan. And this is an area that is going to continue to advance. Okay, so let's make some predictions. That's the easy part of it, right? So let's try and predict the next 10 or 15 years. And what do we know about when we make predictions, right? Well, first of all, it's going to be wrong. So I'm just going to tell you what I think, right? And not make the safe predictions, because it's not going to happen. It's not going to be correct. Again, lots of people are going to be annoyed because whatever they're interested in, I'm not going to say anything about. So again, this is just very personal view, and hopefully people will disagree. Of course, there will actually be some people who are going to be annoyed because I do mention what they're interested in. So sort of guilt by association. And this is what I'm interested in, right? So let's put it out there. This is a very personal view. And, you know, Feynman had this great guiding principle, right, that you shouldn't fool yourself about things. And the problem is that you're actually the easiest person to fool. So it's going to be a sort of eclectic choice based on what I'm interested in. Simple predictions, these are very boring. They're very important, but they're very boring. They're going to happen, right? Computers get faster, more phased arrays, gradients get stronger. We're going to use AI, et cetera, et cetera. It's very, very important, but that's utterly predictable. So if you're going to have a new program coming in, what might you base that program on? So I've talked about what's changed, but what stayed the same. So if we step back, not as MR specialists, and we look at the whole field, what is exactly the same now as it was in the 1980s? Well, there's some sort of trivial things here. Like if you look at the magnet, it hasn't changed, right? I mean, there's been engineering improvements, et cetera, but it's a large cylinder that somebody disappears into, that it's 90 centimeters wide, and whether you're going to image the head or the body or the wrist or the finger, you still disappear into a 90 centimeter cylinder. So the fundamental magnet design is exactly the same as it's always been. And the price is pretty much the same. So the price hasn't come down. Now the systems have got a lot better, but if you want to buy a system, it's still going to cost you 1-2 million euros, right? It hasn't gone down in price. It's like the smartphone, right? The price in the smartphone has actually gone up. Now the functionality has gone up, but still that is not something you can buy a 10 euro or 10 Swiss franc smartphone. You need a large infrastructure, right? There's going to be 7 Tesla. You have a 7 Tesla over here. 7 Tesla goes into Geneva. Everything, the infrastructure associated with that, the shielding, et cetera, et cetera. It's massive. It's a massive building project. An MRI scan takes 30 minutes. It always did take between 30 minutes and an hour. It still takes 30 minutes to do, right? You get lots more information, but it's still a 30-minute scan. It's not a CT. It's not an ultrasound. And you still lose maybe between 10 and 20% of those scans due to a patient moving. So that actually also hasn't changed. And fundamentally, patients hate MRIs. They absolutely hate having an MRI scanner. Why? Because it's noisy, it's claustrophobic, they have to walk in, they have to take their clothes off, they have to get scanned, they have to put them back in, they have to go in. It's horrible. And that has not changed. And let's look also from the societal point of view. Who gets an MRI? MRI is for rich people who go into a large hospital. It always was, it always has been. Right? So there's a societal thing that hasn't changed. The role of MRI within healthcare has not changed, despite all the technical changes. It's always the last process, right? You go to your GP, they do various things, blah, 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 and eventually you will have an MRI. It's always the last process. So there's no MRI in screening, right? It's always what happens last when you go to the big hospital. So that also hasn't changed. And there's a lot of people who can't be scanned due to contraindications, right? Any metallic implants, things like that. So if we look and say, how can we make a big change to the role of MRI, then I think we have to look at what has stayed the same there and to see how can all these technical advances that we've come up with play into that. So if we look at it from the point of view of a world view, 70% of the population has zero access to MRI. There are no MRI machines around. And if we look in developed countries, then again, everything is in a big hospital. So there's the hospital in Leiden in the middle, and as you start going out, you get less and less and less possibilities of MR, but there could be roles of MR, right? Going all the way down to, I don't know, retail clinics, GPs, whatever. This is a Philips slide, so I think you don't go to GPs. It's also interesting, the GP home over there seems to be this massive mansion, so it also tells you something about society. So we've been interested the last couple of years in challenges in the developing world. So again, that idea that 70% of the world has no MRI, and the question is, what can you do about that? So the challenges are, okay, cost starts off, and that's what you think of about initially, and actually that's the least important of it. That you can still have, you know, even in a country which has a relatively low GDP, you still can raise 1 million, 2 million euros for an MRI machine. That isn't the issue. The issue comes when you've got things like maintenance costs, which are going to be hundreds of thousands of euros per year, continually. The fact that you have to have a system which has a large shielded room, it's got to have high uninterrupted power, it's got to have chilled water, it's got to have all of these different components which are necessary for this highly sophisticated MRI machine to function, and your personnel have to be well trained. And these are the things that are really the killers in terms of being able to spread MR technology. So again, thinking about this, what are we going to be able to do as MR technical people to change that situation? The only solution is we have to go to low field MR if we want to look at those particular problems. And we have to go to low cost and low field MR. And that's going to give us some problems, but it's also going to give us, I think, some exciting opportunities. Now, it'd be nice to Siemens, I'll be nasty to Siemens now. So they've just introduced this very nice 0.55 Tesla system. It's a move in the right direction. It's a really interesting system. It's going to have a lot of applications. You can't call that an accessible MRI system, right? It's a 600, 700,000 euro system. It's, you've got all the shielding problems you had initially. So it's a great thing. It's going to help, I think, a little bit in the developing world, the developed world. It makes no difference to anything in terms of a worldview. But if we're actually going to do something, we need to have either new or existing vendors on board, right? We can do this academically, but if we can make partnerships with existing vendors, that's really going to help. And as I said, it's quite an interesting area by itself, low field. Apart from this idea about being able to spread out and change the role of MR in the developed and the developing countries, it's actually a really interesting area of MR. So, okay, how about, again, being pretentious? How about this as the next epoch? Is taking everything that we've developed in terms of technology and seeing how can we take that not to make yet a more sophisticated 1.5 million euro system to go into your local hospital, but actually to increase the accessibility and the sustainability of MR on a more global scale. So how does MR have to change from a technical point of view in order to do that? And how are we going to take things like the sequences developed by people here, elsewhere, the reconstruction, everything that has been designed for a high-performance system, how do you take that to a system which is much lower performance? Right? So how do you enhance the performance of the low one? But this is not a very, very simple translation. Right? You can't simply take what you've developed up here and apply it down to a low field. So how can we build sort of a new area where we specifically say, here are the properties of a very low-cost, low-field MR. Let's try and develop everything that will take that to the highest possible image quality. So here's the low-field current state of the art, because you're probably just used to seeing high-field systems. So what is state of the art in terms of the labs around the world at the moment? So let's look at some of the advantages anyway. Okay, no sighting costs. So the magnet that I'm going to talk about in detail, the one we developed, will basically fit on this table over here, right? So the portability is about 70 kilos. You can sort of move it around. So sighting costs, you want to sight it, you put it on a bike. I'm from Holland, right? You put it on a big bike and you cycle it around the corner and you put it over there. You plug it into the wall, you don't need any cooling. Susceptibility effects are very small, and where that's important is really medical implants. So you can actually image ferromagnetic implants. The force, which would normally be very damaging, of course, to the patient, is so much less at low fields. So people have metallic implants, no problem. Which also means you don't have to have everybody coming in and ripping their clothes off and taking all the checks and seeing if they've got implants, all of that. You can get rid of that. The SAR, this is the power that is deposited into the person, which obviously, which sometimes is a limiting factor when you go up to high field, is thousands of times less. And that means we don't even have to worry about it, but it also means that as we design our sequences, we can really put a lot of power into the person. And that means we can get a more efficient in terms of the signal that we can get out. Things like wires that are left inside, pacemaker leads, etc. It doesn't matter. They'd have to be 75 meters long inside somebody to actually cause a problem, right? So we're pretty safe there. Gradient noise is out, it's silent. Right? So again, if we think about one of the issues where people hate scanners, they're very loud. This one you can't hear. And from an MR point of view, then we have some advantages in terms of our relaxation times. We're able to pulse more rapidly, and there are, again, not to go into too many details here, but it means that some of the sequences we typically use are very, very efficient. So there's lots and lots of things which are potentially quite good about going towards low field. So here's some of the systems that exist around the place. So there's a very low field system on the top left there from Matt Rosen's group in Boston. So this is only 6 milliteslas. This is tiny, tiny field. It's actually inside, it's not a portable system. It's built inside a Faraday shielded room over there. But as I'll show, his group was really the one who showed you can get useful images at really low fields. Lower fields, I think, than any of us thought were possible. We have a group in Aberdeen with David Lurie then, who actually has a magnet that changes in field. So it can go anywhere between 1 and 200 millitesla. It's a really, really interesting research system. We have then a company, Hyperfine. I'll talk a little bit about, show some of their images. They're at 60 millitesla. Again, they have a system, it's about 700 kilos, but it's on wheels, so you can move it around. And then we have 2 developed systems, one Boston, so this is Clarissa Cooley's group, and our own group in Leiden, which I'll talk a little bit more about. And these are, as you said, between 50 and 80 millitesla. And to give that means we're operating at 2 megahertz or 3 megahertz. Right, so we're operating it's like an ultrasound system in terms of actual operating frequency. And then again, the portability, this is one from a Japanese group. You basically put it in the back of your car, drive it around, things like that. So that's the idea. So these are the systems that currently exist. So just to give you some idea, again, this is, so Mathieu Sarkany, who's now in Basel here, was the first author on this paper where using the SSFP sequence, very, very efficient sequence developed by Klaas here, that we were able to get images in a few minutes. I think this is about 6 minutes over here. And again, this is 6.5 millitesla. This is not a 7 Tesla or a 3 Tesla system. Now, is it as good as a 3 Tesla system? No, and it never will be. The basic physics is going to be against you. But can you get something that if you're competing not with a 1.5T or a 3T, but with a nothing, because there isn't anything there, this is going to give you extra information and quite useful information, right? So, and of course, that group has continued to be very active. There's another group in China here, just published a paper at the end of last year where they were looking at stroke patients over here. So this, ignore the CT over here. So this is the MR. And again, you can see areas over here which are clearly showing the stroke. And this is operating at 2 megahertz. So again, a very, very low field system. You can see it looks a little bit like that old Philips system in terms of being from the construction. Hyperfine is the most successful company, so they have raised an enormous amount of money, and they're based on the East Coast in the US. They hired all the Philips engineers away to go and work for them. And they essentially have, again, a system which has has a magnet at the top, magnet on the bottom, say about 700 kilos over here. But you see these kind of images here, which are at 60 millitesla, are sort of quite similar to the initial 1.5 Tesla systems we might have seen back in the 1990s. The advantage here of these magnets is they have no fringe field. So you can take that and you can put it up right next to a patient. So actually the way they've designed it, you can see here is the patient bed will actually dock so that somebody in the ICU, somebody who can't be moved, the magnet can be wheeled up and docked with the hospital bed there. So this, in a sense, is sort of, from a commercial point of view, state-of-the-art in terms of low-field imaging. But, okay, now I've been nice, so it can now be nasty. It's very, very heavy. The electronics are complicated, and it can't be repaired. Right? So one of the things I want to come back to is how do you design things sustainably? This is not sustainable. It breaks, the engineer has to fly out, has to fix it, etc. But in terms of really showing this is a valid concept, both from a commercial point of view and also a scientific point of view, this company has played an incredibly important role. And again, a number of studies that are coming out now by studying many, many patients with different diseases and different conditions. And as it says, it's the bedside of critically ill patients. There's no way you're going to take this patient and wheel them into a 1.5T. So again, you're getting extra information you simply couldn't get other ways. Let me jump over this. So these are the type of system that we're interested in, truly portable. So things that are between 70 kilos and 100 kilos. This is a group from Boston here. They have a particular design which actually has an inbuilt gradient into the magnet, so they don't have to do full gradient encoding. A number of papers there. And you'll see these are the kind of images that they're getting out. So again, the signal noise is pretty good. You can see there's quite a bit of distortion over here. And this is part of the reason is they have this inbuilt gradient, which is very difficult to overcome. So we actually use a different approach to the one that they did. But it's quite an elegant way, again, of low-field imaging. So let me talk a little bit in more detail about the project that we've designed in Leiden. So we were approached by a pediatric neurosurgeon in Uganda, who works in Uganda, who studies hydrocephalus and treats kids with hydrocephalus. And essentially what he wanted to do is to see, is there a non-invasive way of following after surgery, after removing the excess fluid, the CSF, of seeing if there's any blood left in the brain or indeed if there's any fluid left in the brain. This is a condition that doesn't really exist in the developed world, but it kills tens of thousands of kids in the developing world. And so where is the fluid? That's all you need to know. It's a perfect MR problem, right? You don't need incredibly high resolution. You don't need incredibly high contrast. But it's a clinical problem that we should be addressing. And we can't address it because there's no MRIs around in Uganda in this case. So we set up a collaboration to work with the Children's Hospital, but also with the engineering department, which is associated with the hospital. So, as I said, hydrocephalus, you'll see, it's everywhere that we're used to, it doesn't exist. The areas where it's very strong, then is also the areas where there is no MRI. And again, what we want to try and do here is not be the sort of imperialistic Western world coming in and building something and plonking it down in the middle of Africa. We want to try and design something which can then be produced locally, that knowledge can be transferred over, that we don't say that, oh, the software needs to be upgraded, you know, it doesn't work anymore, or if one of the gradient amplifiers breaks, sorry, you have to ship it back and we have to repair it and when we ship it back to you. Right? We want to try and get a system, design a system, which is going to be a good MR system, but is also sustainable and is repairable and is fixable, upgradable, etc., at a local level. So we have regular meetings here. So this is something where we're taking our technology. Every Monday morning, we have a Skype meeting with the engineers over there in terms of they're rebuilding the system that we have, and then they're improving the system as they see how it operates, you know, in quite challenging conditions. So again, the idea of sustainable and repairable. So here's the magnet that we built. I'll show you details in 1 second, but this is, you know, a system which is this big over here. Like I said, it will probably just about fit on the platform over here. It's made of thousands of very small magnets. So you can buy these in the supermarkets. You can buy these, you know, they're about 20 euro cents. I'm not quite sure about the conversion factor to Swiss francs, but it's pretty cheap. Total about 4,000 euros here. And the thing from an MR point of view is that the magnetic field is this way. We're used to magnetic field being along the bore, but the magnetic field is side to side, which means we have to redesign some of the electronics and some of the coils and things like that. So this is how we built it. And again, the idea was that we want to use very small magnets so it's safe. So these are strong magnets, but if you get your finger stuck between two of these, you're okay. Right? If you take some of these big permanent magnets and you get your finger stuck, then you don't have a finger anymore. So it's got to be very, very easy to make. It's got to be safe to make, so this is why we go for these small ones. We want to not have very, very expensive components. So these magnets, you know, they're plus minus 2 or 3% in terms of their field strength. That makes it cheap. So we want to use lots of them, as they say, 2,948 in this magnet, so that those imperfections are averaged out. So a little bit here, we're putting it into plastic, right, that can be cut, so it can be machined locally. It's held together with brass rods, et cetera, et cetera. So it's something that is a pretty simple design. So this is what we have then. So we have the magnet on the outside in blue. Then we have little shims in there, which are the same construction with permanent magnets. Then we put the gradient coils in. And again, gradient coils come off standard 3D printer, just with wire put around into those grooves. So something like on the right-hand side, again, relatively easy to construct. We have specialized gradient amps and RF amps, so they don't have to be very powerful. They're not water-cooled. RF coils, again, very simple in terms of design. Either for the knee or head, and here's our integrated setup. Right, so our shield, our Faraday shield, is basically a conducting sheet. Over here, you can see a cloth, and then it's into just an aluminium cage over there. So here's the entire setup that is used for imaging. To give you some idea then, image quality here, this is some relaxation time mapping that we were doing to get T1 maps and T2 maps, and we can do fingerprinting, we can do all kinds of things, standard sort of sequences here. And so this is just published, I think, last month. And what this allows us to do is to basically do image segmentation here, so we can look at where is the CSF, where's the white matter, gray matter, because one of the things that we're interested in is pediatric development. I know Mickey's going to talk a lot more about pediatric imaging this afternoon. But within Africa, how does the brain, in many, many different genetic makeups of populations within Africa, how does it develop? And you can't image somebody in a 3T, you know, once every 2 years, because A, there isn't a 3T, and B, you don't want to be putting kids into these kind of systems. You have a system where essentially somebody lies down, low field, no magnetic effects, it's silence. You know, the parents can come and hold on to the hand of the child as they're being imaged because there is no stray field, etc. It gives you a lot of opportunity, not just clinically, but also in sort of basic population dynamics. So, okay, images going through. The reason I show this is the lower leg, is one of the other projects we're working on is malnutrition. So malnutrition then, one of the ways of studying that is simply by imaging one of the limbs, typically the forearm of kids, and then again you can look at how much lipid there is, how much fat there is, get quantitative measure very quickly of malnutrition, which is actually, apparently, I'm not an expert, quite difficult from the outside to get a sort of quantitative measure. Okay, the other thing then at low field, and this is just an example, is that if you've got medical implants in there, metallic implants, that you can still image those because they're safe, and also the image artifacts that you get are much, much less. So if you look at the top row over there, you can see that even if you have this pedicle screw, this is a big screw that's used for spinal surgery. If you look at a 1.5T or 3T, the image is destroyed around it. And if you look at the one at 50 millitesla, you can actually see the spiral around that pedicle screw. So this is what you'd expect, but it's a nice demonstration of what's possible. And again, what we want to do here is to have a sustainable engineering design, so everything that is on that system is open source. So you go to GitHub, you go to whatever repository, you can rebuild, anything goes wrong, you can rebuild your amplifiers, and if you want to build a magnet, you've got all the code to build the magnet, and you've got the code to build the gradients over there. And you know, one of the things that is always brought up is, yeah, this is very nice and very naive and everything like this because we want to get companies involved. But there are now constructions being put together where we can look at being able to open source hardware, things like that, but also within a legal environment where companies can come in and make profits if they are licensed to these kind of things. This is a recent thing just came out last month in terms of, and the MR community was actually quite well represented here to try and show how that works. Okay, so to come back a little bit then, how does this fourth as I said, rather pretentious idea in putting forward to work out, so how do we take all of the things that we've developed as MR people, and how do we try to make accessible MRI better? And how do you do this as a scientific thing, right? If you think about this as a scientific program, you don't want this very fluffy stuff over here. You want to be in engineering, you want to be in physics. So you've got to do things from that point of view. So what are our challenges, right? Number one, low signal. Really, really, really low signal. That's our problem. That's the physics of it, right? That's what we have to overcome fundamentally. Also, no shielding, right? So no shielded room. So somebody starts a power drill over there. You've got the signal coming in over here. We've got to get rid of it, and we're not going to build a shielded room there. Our gradients are weak. So a lot of what we've been developing in sort of optimized case-based coverage and great SSFP sequences, this, that, or the other, assumes you've really got some good gradients there. Strong gradients, fast-switching gradients. We're not going to cool our gradients. So we're going to have to design things around very, very weak gradients, ones that don't switch very quickly. The field homogeneity is small, is poor, right? I want a small magnet that the head just goes into. If I made the magnet really, really big, I could get much better B0, but it would be even weaker, so much lower signal, and it would be much heavier. So we want something that's portable, and that means that our magnetic field is going to be inhomogeneous. So we have to deal with sequences, not which, if you read the literature, we have some sequences that deal with poor B0. That's not poor B0. We'll show you poor B0, right? So you have to think about that. Electronics are simple. We would like a one button, run, go, right? Turn the MR into an X-ray machine. And I'll talk a little bit, give some examples of work from here as we go through this. Spatial resolution, we're not going to be at 0.1 millimeters. So we're going to be at 0.5 millimeter, 1 millimeter. So what does that mean? It actually has quite a lot to do with how you acquire your data. Because things that are important in terms of motion, et cetera, I don't care, right? So how are you going to design your sequence if you've just got low spatial resolution in mind? Lots of opportunities for doing different things. And the magnet is going to drift. If you really want to take this out in the field in an African village, the temperature is going to go up and down 20 degrees. That means the magnetic field drifts in real time. So how do you deal with that? Right? We're going to have some feedback control there. We're going to change the acquisition, or we're going to try and stabilize the magnet. Again, lots of problems. Did I mention it's really, really, really low signal to noise, right? This is really the problem that we have to face. Our amplifiers don't have much power coming out of it, right? Our coil geometries are different because the magnetic field's in a different way, so we have to rethink about that. If you're an RF engineer, these coils couple to each other. There's no patient loading whatsoever. So all these schemes where we assume that this coil doesn't couple to this coil, doesn't couple to this coil, gone. So can we redesign all our image reconstructions, maybe along the way that a radar does, where everything couples to each other? We can characterize that coupling. Can we then deconvolve that coupling in terms of our image reconstruction? Our coils are so high Q, big problem, right? Normally we have the problem our Qs are very, very low quality factors. Our Qs are too high. And that means that with respect to the imaging bandwidth, often the bandwidth of the coil is smaller than the imaging bandwidth. So how do we overcome those kind of problems? So there's a quick list of everything that is problematic, but everything that is a challenge and everything that acts completely opposite to what we used to in terms of how we design our experiments and how we've done the optimization within the last 30 years. So we've got these great electronics, right? Hardware design, sequences, et cetera, This is developed by many of the people who are going to talk after me. None of those have been considered for low field, right, at all. And you might just say, well, isn't it pretty easy, right? So just take your T1, T2 times. They're different, but who cares, right? And the coil's this direction, that direction, who cares? It's a pretty simple problem. And you could say that, but then I would say, being Dutch, okay, you don't have much imagination. If you're just going to use everything that's been developed and just say, let's translate it down, A, that is very boring, and B, you won't do a very good job. So it's a fundamentally different regime that we're in, and it gives us fundamentally different opportunities, I think, from an imaginative point of view, to do things in a different way. So let me just throw out some ideas about what we're thinking about, and what, again, I think could be a good research program. So things like fingerprinting. We want to do that. We want to very rapidly estimate our relaxation times, because from our point of view, that's actually going to help us in segmentation. And what's interesting there is if you look at all the kind of standard sequences in the blue over there, the patterns look pretty much the same at high field. You go to low field, the patterns look totally different. Now, in a way, that's a simple thing, right? We can just optimize it. So that's the example of something that's a little bit boring, but actually comes out with something which is a different way of doing things. But there are fundamentally different things. So lipid suppression, you want to get rid of the fat signal, all right? This is all clinical MR. You want to get rid of the fat signal, how are you going to do it? Different relaxation times, well, they're the same at low field, so you can't do that. Chemical shift difference doesn't exist. It's 2 hertz, something like that. You can't do that. So you can't do any of the standard techniques. So if you're somebody who likes designing MR sequences, how are you going to get rid of it? You might think about magnetization transfer, which is very different from lipid to tissue. You might think about diffusion, because lipid doesn't diffuse very fast, whereas with tissue, water does. So you can sort of incorporate different ideas from areas we haven't looked at traditionally in terms of lipid suppression. Magnetization transfer, example, no SAR. You can put a large pulse on for as long as you want. You could use it for lipid suppression. You could get incredible contrast with tissues with magnetization transfer. You could look at things like inhomogeneous magnetization transfer, which is a technique which is not much used at high fields, but actually has a lot of advantages at low fields. Might be useful, again, for tissue contrast. We're going to have trouble with diffusion weighting because we've got weak gradients. So can we find surrogates for high B factor diffusion weighting? Maybe they're relaxation parameters that show similar contrast in things like stroke, things like neuro diseases. Spin locking sequences are, again, something that we think about in terms of contrast, not often used, because they take a lot of power. We don't care. T1 row is often thought about as T1 at low field, but we are at low field, so we're going to be at ultra, ultra, ultra low field there. So lots of new possibilities there in terms of image contrast. And then let me just give one specific example, spectroscopy, right? Something that we typically do at high field, and you think, well, you can't possibly do that at low field, right? Why can't you? Well, if we look here, so this is work by my colleague Itamar Ronan from last year. Here's the line width of your water peak here. It's 500, 600 hertz. And what's your chemical shift in terms of if you're looking at lactate? Let's say we're looking at brain tumors and lactate, right? And the difference between lactic acid and water over here is like 6 hertz. So there's no way you can resolve it. So spectroscopy is impossible, right? Well, it isn't. What's interesting, if you go back to quantum mechanics, is that if you look at our normal spectrum over here of, in this case, so lactic acid, right? That's standard CH3CH over here. Go to low field, everything changes. This is the spectrum at low field. Why? Because we have what's called a strong coupling system. And that means that the chemical shift and the J coupling are very similar. And that totally changes the behavior in terms of what that spin system does under different sequences. So you go back, luckily being old, you remember things like this from the 1980s. And these are different sequences which look at refocusing scalar coupling and not refocusing scalar coupling. Again, skip over the details, but this is what you can get out. If you're on a CPMG train, you just run a whole series of pulses on the left-hand side, you'll see there's modulation on that signal. If you Fourier transform that modulation, you get distinct patterns over here, and this comes from lactic acid. And look at the frequency resolution there, 1 hertz. So by looking at sort of different kinds of sequences here, we can actually do experiments which would need a simpler sequence at high field. But we can get, in this case, information that you might think at first sight is impossible to get out. So lots of opportunities from a sort of MR physics point of view about doing things. I said something about simplicity. This is what I want, right? On, off, X-ray, over here, right? So very simple system, not do I angle this, do I do this, do I do my localizer, do I do my et cetera, sequence. So we have to get to that kind of point of view. And so I'll invoke what I call the Peter Burnett philosophy, which is essentially sample like hell. Right? So Peter's a Philips guy over at Hamburg, very, very influential in the development of many aspects of MR. So I get to share an office with him 3 days a week. He comes over to Leiden. And this is what he says. Just sample. Start. And I want to pull some work here, which comes from the EPFL, which essentially, in a very complicated system over here, looking at cardiac imagery, takes the same principle, which says, I don't want to have somebody going in there and sliding in and planning this part of the heart and this part and this part. Put them in, scan like hell, we'll deal with processing afterwards, right? And making something that simple is really, really difficult. Ask Matthias back here. It's very, very complicated to make something look simple and come up with high quality data. But that's what we have to do, right? We have to not have a trained technician who has to be able to do this and this and this. The kid has to go in, stay there, sample. If they move, you have to deal with it. If they move out, you have to deal with it, right? Just sample as fast as possible and deal with things afterwards. Last couple of minutes then, things like temperature compensation. So how are you going to compensate for temperature? Well, you might have an idea where you have temperature sensors around in there. You might then say that it's going to be inhomogeneously distributed. You have come up with some kind of nonlinear image reconstruction, which is going to build in the fact that these temperatures changing different rates at different times of day, et cetera, et cetera. Noise suppression. So this is some work coming from the Cooley group and also Will Grissom in Vanderbilt. So here's a typical thing. If you don't have any shielding, that's your image at the top row over there. So how are you going to correct for it? They are using external sensors over here. So this again just published last month. Some pretty impressive results over here by using external sensors and canceling things out like this. So this is what we've got to be able to do. We have a slightly different approach over here where we actually take an RF coil and we detect the signal, but also part of those modes from the RF coil are only sensitive to noise. They're not sensitive to MR. And so we can do a very simple subtraction technique here just using a single coil where we can get rid of the external interference. So these kind of ideas, again, coming into the idea, it's an electrical engineering position that you're talking about, right? So how can we develop these kind of things? AI, I think, has a big role in terms of noise suppression. Phased arrays, you want to accelerate things, except our B0's in the wrong direction and everything couples together. So how are you going to overcome that kind of problem? That's a fundamental engineering problem to consider. We're at low resolution. Can you take some of these ideas with coil arrays that Jürgen Hennig developed over the last 15 years and use that in spatial encoding, right? So could we build 64 coils around there and just say, forget gradients, we'll do a 64 by 64 image. So that's the kind of thing Steve Wright did many, many years ago, because we're not trying to get 256 by 256. So incorporate that into image reconstruction, etc. The real game changer, which I'll finish with, is you can now design your own magnets. Right? So for the last 30 years, we don't design our own magnets. We buy whatever comes with it. It's cylindrical, whatever you're going to image with it. If you've got the opportunity of buying 5,000 small magnets, you can make whatever kind of magnet you want. And based on that magnet, you can build whatever gradients you want, you can build whatever RF you want, and you can build whatever image reconstruction you want. So you can integrate everything into totally different kinds of magnet designs. So here's some examples of what we're working on. So, head magnet. Eyepieces over here get rid of claustrophobia. It's like those old-fashioned, hair dryers that come over somebody, like this. You can build something like that. You can build magnets that open up. So you can have something that will be from MSK. You can build a magnet that just closes around the particular area. Maybe it closes around the Achilles tendon. Maybe it closes around the knee. You can look at lung imaging. So maybe relevant for COVID. I don't want to bring up the COVID thing here, but just in general, lung imaging. Again, you can have an upright magnet that opens up, somebody sits in, it's like a sort of mammography type of system. You can even think about going to things like surface magnets. So if you have a surface magnet, this is over here, then you can take a surface magnet, you can put optical sensors on it, you can follow the optical sensor, you can take the magnets and the clinician can be moving around like this and you can reconstruct with superposition principles. You can even think about doing magnets on somebody running. So if you want to follow what's happening in terms of exercise, what's happening to the muscles, put the magnet on here. The magnet moves with the person, so you've got dynamic MR. Okay, it all sounds like science fiction. That's actually what the grant reviewer said when I put in the grant. So if you read here, the second line, it says, blah, 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 blah. It sounds like science fiction. If you write that in the NIH in the States, you're dead. The nice thing here was the person said, this sounds really cool. I don't believe it, but give him the money and try it out. fMRI, I mean, think about somebody with a magnet over here talking to somebody with a magnet over here through this things over here. But you can't do fMRI, right, at really, really low field. Well, there's a paper with a certain Klaus Schäffler on it talking about low field MR at 0.1 millitesla over there. Possible, interesting to think about, be a very, very cool experiment. You think about other things like multi-frequency switching. So it takes the ultrasound idea. And as you've got an inhomogeneous magnetic field from the surface magnet which is placed on somebody, that means that the alarmal frequency changes. So just excite frequencies as a function of time and build your image up there. So borrow this kind of dynamic focusing idea from ultrasound. Lots and lots and lots of different things that is, I think, possible to do. Fundamentally different MR, with the idea of increasing accessibility, increasing sustainability, You know, you can even take your magnets and rotate your magnets and change your magnets, etc. How does AI fit into this? Again, because it's obviously an area in terms of denoising, yep, you can do work like that. I think the role of it should not be overemphasized here. It can help. Let's not get carried away, right? Pair of binoculars plus AI does not equal the Hubble telescope. And equally well, what a lot of people, I think, say is that now there's so much processing power, it doesn't matter what the hardware's like. You can say the hardware's crap, I know what it is, I can build that into my reconstruction, I get high-resolution images over there. It's not true, right? It doesn't matter what it is. CNN, GAN, adversarial, insulting, really annoying, whatever that algorithm is, you do not turn the image in the left into the image in the right, which is when you build the hardware correctly there. I think that's an important lesson. I think Mickey may also talk about some of the dangers, you know, in terms of AI. So it's an important area, but we don't need to get carried away. So the role of electrical engineering, the role of physics is incredibly important. And we finish there with current support and then previous support here and the team who has done the work. Thanks.
You can keep it for questions.
Thank you very much, Andrew, for the very fascinating, motivating talk. We have time maybe for a quick question. There will be a panel session at the end of the day, so we can go more in the details. If you have detailed questions to Andrew and to the other speakers. Do we have one quick questions in the audience? Please. Yes, please. Wait. There are people online.
I will take out my mask like this to talk with a human being. I'm Christina and I'm a spectroscopist. So I was wondering, I'm a high field spectroscopist. I'm not a low field spectroscopist. So are there papers with spectroscopy at low field?
There are
a lot of, you also showed now a lot of imaging papers on low field MRI. But is there something published on spectroscopy at low field?
There's very few papers.
Very few papers.
I think there's probably 2 or 3 papers. We hope that will change.
Okay.
Because I think, as I said, you cannot use the standard direct measurement techniques that are used at high field, simply because the spectral dispersion is not high enough. So you have to move to these indirect techniques. Those have traditionally been two-dimensional, right? So there's a long history of two-dimensional indirect, and those take too much time. The idea here, I think, is because you can really run a very, very long echo train, you can effectively turn that two-dimensional matrix into a one-dimensional experiment, which means you can do it fast. So what I hope is that we can look at some of those two-dimensional experiments which have been carried out in inhomogeneous fields, turn it into a one-dimensional equivalent, and that will mean that it is now feasible to be able to do in a reasonable period of time. But there are very few papers at the moment on that, yeah.
Thank you.
Another quick question, Matthias? Yes.
Thank you very much, Andrew, for this wonderful presentation, which I think resonated very well with many of us in the room.
Good.
No pun intended. If you're thinking about the vendors, how much enthusiasm or nervosity does this create in the vendors' minds? What is your thought there?
I'll tell you about one vendor, which you will guess and I won't name, that came in and essentially, you know, said, this is way too early, so we are not interested. And also it might destroy some of our market, right? Let's say that's 3 years ago. 2 years ago, they come in and say, well, we're slightly more interested because you're getting images out of it. And then you start to see the interest grow and grow and grow, right? And I think particularly, I have to say, if you look at the fact that it might change what is seen as the role of healthcare within, whether it's the Netherlands or Germany or Switzerland or whatever, then, you know, we have to accept that they want increased market share and increased sales. And you can't take away from existing sales. So if you open up new markets, whether that be an interventional MR, how you've designed the magnet as a flat magnet for the patient to be on, or whether it's you can now sell those to orthopedics and to smaller centers, that's what they're really interested in. So that's why I think that's what we have to concentrate on from that point of view. So there is a growing interest, I think, from them, but it is going to be driven by opening up new markets and new opportunities.
Okay. Thank you very much. Okay, Andrew, thank you so much for the talk again. Let's thank the speaker again. Thank you very much.